Hi students, in the last class we were discussing about the distributable particles and their distribution function, and after that we came to quantum statistics where we discussed about the symmetric and anti-symmetric wave functions, and these wave functions are associated, the fermions and bosons, they are indistributable particles and their wave functions overlap. So within this, your bosons, they have a symmetric wave function, and fermions are an anti-symmetric wave function. And also we look at the probability density of occupancy of two particles in the same state for the bosons and also for the fermions. We understood from our expression and our calculation, mod psi square for the fermions is equal to 0 if both the particles are occupying at the same quantum state. So that is a clear indication that you cannot occupy more than one particle at the same quantum state for the fermions. That is nothing but the Pauli's exclusion principle. And for the bosons, what is mod psi square is equal to 2 times the mod psi m square. That is for the twice the probability of distributable particle in the case of bosons. That we understood. We were at that stage. Now we want to go to study what is the distribution functions for the bosons and also for the fermions. Or basically we already told in the first classes, you can have Bose-Einstein distribution for the bosons and Fermi-Dirac distribution for the fermions. Okay, so we will look what is this and how it looks and what are the properties of it, that we are going to discuss today. Okay, so first I will just write Bose-Einstein and Fermi-Dirac distribution. So I am not going to derive it because it is beyond the scope of our syllabus. We need the expression and we will discuss the properties. That's it. So first we will go for the bosons. For the bosons obey Bose-Einstein distribution function. So I am just writing bosons obey the Bose-Einstein distribution function. So this f of epsilon, maybe you can write FBE, it's a suffix if you like. Nothing wrong with it. This is the probability that a particle occupy at a quantum state epsilon. F of epsilon is equal to 1 by e raised to alpha e raised to epsilon by kBT minus 1. Okay, where this alpha, it depends, the quantity alpha depends on the properties of the particle under consideration, and it is generally a function of temperature. And now we will go for the Fermi-Dirac distribution function. Fermi-Dirac distribution function. So how? Here also, if you like, you can just put F here, means Fermi-Dirac distribution function. That is the probability of a particle occupied at a state energy level epsilon, okay, equal to 1 by e raised to alpha e raised to epsilon by kBT plus 1. So this is the difference. Here you have minus 1 and here it is plus 1. I will tell you what here minus and why here it is plus. Okay, and here also this alpha, whether in this or in this wherever, this alpha, the quantity alpha depends on the properties of the particle, and generally this is a function of temperature. Okay, so this is the things. Now first we will go for Bose-Einstein distribution function. So in the case of a Bose-Einstein distribution function, in this expression you have a minus 1. Actually this minus 1, it increases the likelihood of occupancy of multiple particles in a condensed state for bosons compared to the likelihood of occupancy of particles in the case of a distinguishable particles, like the particles which obey Maxwell's Boltzmann distribution problem. Okay? So actually in the denominator you have a negative minus 1, means it actually increases the probability of f of epsilon, isn't it? Okay, actually this reduces quantity so that you will increase this f of epsilon. Okay? And in the case of Fermi-Dirac distribution, you have a plus 1. Actually the fermions, you know, it obey the Pauli's exclusion principle, and whatever may be the value of alpha, epsilon and t, you should not increase the probability of f of epsilon more than 1, or you can say the maximum value should be 1. It should not go beyond that. Okay, so that means the maximum occupancy should be, the probability should be 1. Okay, so that you can see, if you take here this quantity as something like totally it is coming 0. If you have a combination, this is coming 0. In that case also you must have the quantity maximum of 1. It should not increase. If we have some value, so obviously it become less than 1. Okay, here there is some quantity plus 1. So 1 by that one always less than 1, and the maximum value for this probability should be 1. Okay, so that is why here the Fermi-Dirac distribution function you have a plus 1. Okay, now we have to go for more and more properties of it. So we will check it one by one. And another interesting thing is, if epsilon is very greater than kT, if epsilon is very greater than kT, you can see, if epsilon is very greater than kBT, in that case both the expression converges to our Maxwell-Boltzmann distribution function. Okay, so if epsilon is very greater than kBT, that means what will happen? This one will be comparatively small, or you can neglect it, isn't it? Here also you can neglect this one, because this quantity is very high. Compared to this is small. This one you can discard. Here also this one you can discard. So eventually it will return to f of epsilon is equal to a raised to minus h1 by kBT. That is our Maxwell's Boltzmann distribution function. So that is the thing. That is, if the energy of the particle or the energy level is very very high, then in both the cases, whether it is Fermi-Dirac distribution function or Bose-Einstein distribution function, it converges to, or it will become simply Maxwell's Boltzmann distribution function. That is the distribution function for the distinguishable particles. If you draw the distribution function versus epsilon, the energy for these three distribution functions, how it comes. So you have to keep in mind, when you find the probability density, which one has the highest? The highest one was for the bosons. Okay, then the maximum is getting 1 for fermions, and the Maxwell-Boltzmann is in between. So we will draw it. So we will just this is your y-axis and this is your x-axis. On the x-axis you have epsilon, and on the y-axis you have f of epsilon. Okay, so if you draw this, I am just writing the energy here, K1 kT, 1 kT, 2 kT, 3 kT, 4 kT, and 5 kT. Here you have 1, 2, 3, 4, like that. Okay. So one thing is clear for you: for the Fermi-Dirac distribution function, the maximum value, the maximum probability is 1. And another important thing, when epsilon is very very greater than kT, all the distribution functions converges to Maxwell-Boltzmann distribution function. So you can draw something like this, like so this is f of Fermi-Dirac, because it has a maximum of 1. Now if I take another color, then this Maxwell-Boltzmann will come around this. Maxwell-Boltzmann, and the final we will write the Bose-Einstein. Bose-Einstein will come like this. Oh. This is Bose-Einstein distribution function, which is Maxwell-Boltzmann and Fermi-Dirac. So this is the way how the things are changing. So here, if you draw it, you will get it like this. And here one thing is clear: Bose-Einstein distribution function, that is FBE of epsilon for the bosons is always greater at a given ratio of epsilon by kBt, then it is for the what is called the distinguishable particles like molecules. And one more thing, here you have the Fermi-Dirac distribution function. This will get half for an energy of epsilon is equal to this. We will write the expression of epsilon for the Fermi-Dirac is equal to 1 by e raised to alpha raised to alpha by dt plus 1. This was for the Fermi-Dirac distribution function. So if your epsilon, okay, epsilon is equal to, if epsilon is equal to minus alpha kbt, then what would be? Then you will get this epsilon is equal to half, because when you substitute it here, kbt gone and e raised to minus alpha, e raised to plus alpha into e raised to minus alpha, so e raised to 0, so that will become 1, and that will give you 1 by 2. Okay, so now let us consider a system of fermions at temperature T equal to 0. So what is the situation? Okay, in this case, if you investigate it, the occupancy of states whose energies are less than epsilon f, we call it as Fermi energy, because here wherever we given epsilon, actually this be the distribution function that you are getting half, that we call it the point where you put the Fermi energy. Okay, I am not discussing much about the Fermi energy and all those things, because it is a great notion and you have to understand everything about this. Okay, for the time being you just understand like this. So here if you consider a system of fermions at T is equal to 0, that means here absolute temperature equal to 0, and investigate the occupancy of states whose energies are less than epsilon f and greater than epsilon f. These two situations we will look at, because you have this will half at this point, epsilon f equal to epsilon equal to epsilon f, where you got Fermi-Dirac distribution function equal to half. Now we will look the system where your energy is less than epsilon f and greater than epsilon f at absolute 0. That we have to see. Okay, so we will look at it. So here I will just rewrite our distribution function. Okay, f of epsilon is equal to, I am writing it for Fermi-Dirac. Okay, Fermi-Dirac that we are going to discuss much more. 1 by e raised to alpha e raised to epsilon by kbt. What about Fermi-Dirac, whether it is plus or minus? This was plus. And what you got? If epsilon is equal to minus alpha kbt, then you are getting, okay, I will give me a step. If epsilon is equal to epsilon f is equal to alpha kbt, then you are getting fd of epsilon f is equal to half. Okay, that we got it. Now from this one I will write alpha is equal to what? Alpha is equal to minus epsilon f by kbt. Okay, I will substitute it back. Then f of epsilon is equal to 1 by e raised to epsilon minus epsilon f by kbt plus 1. Okay, so what you need? You need to study about this for the value of epsilon which is greater than epsilon f, that is the Fermi energy, and less than epsilon f, that is the less than epsilon Fermi energy at absolute 0, at t equal to 0, that we want to study. So we will look at it and just revising. I will just write the final expression as like this. So here I will write e raised to epsilon minus epsilon f by kBT, kBT or kT, okay? Because from lower classes I used to say kBT to distinguish the different constants. Okay, so here Boltzmann's constant k, I wrote kB. Okay. Now, what I told, at temperature T equal to 0, first we will take it consider epsilon is greater than epsilon f. In this situation, what would be your what is called Fermi-Dirac distribution function? Okay, that we want to see. So here f of epsilon is equal to, here epsilon is greater than epsilon f. So this is a positive quantity and this total will be a positive quantity, isn't it? Okay, so I will just write f of epsilon is equal to 1 by e raised to epsilon minus epsilon f, that is a positive quantity because this is greater than this. And what about t? T is 0, so 1 by t is infinity, so e raised to infinity plus 1. So what about this value? Do you have any value for this or not? Because 1 by e raised to infinity, e raised to infinity is again what you will get. This is a very huge value. Okay, very big value. E raised to infinity. This is not alpha, this is infinity. E raised to infinity is again an infinity. So 1 by this will give you what? Equal to 0. And what about the other hand? T equal to 0 and epsilon is less than epsilon f. In this situation, f of fd at epsilon is equal to, here you look at it, because epsilon is less than epsilon f. So epsilon minus epsilon f will give you a negative value. Okay? And this is negative, and 1 by t is 1 by 0 is infinity. So you will get e raised to minus infinity plus 1. What about this value? This value is, here e raised to minus infinity, that will give you what? 0. Because 1 by a huge value, that will be 0. So 1 by 1 we will get 1. So then, what does it mean? What is the meaning of this? At the same temperature, that means you are considering the system at the absolute temperature, and when the energy of the particle becomes greater than this epsilon f, your distribution function becomes 0. That means you don't have any particle occupied at all at this energy level epsilon, isn't it? And at absolute temperature T equal to 0, when epsilon is less than epsilon f, that means whatever the energy level that is less than this epsilon f value, your distribution function giving 1, because for the Fermi distribution function the maximum probability is 1. So the maximum value you are getting at t equal to 0, at absolute 0, if your energy value or the energy state of the particle is less than epsilon f. That means Actually, this is what is called the barrier between the occupied state and the unoccupied state for fermions. Okay, that means you can in simple words, at absolute zero, the occupancy at absolute zero, the occupancy has a maximum value if your energy level, the energy level value is less than Fermi energy. The occupancy value or the probability of occupancy is 0 for all the energy values which are higher than the Fermi level. That means at absolute zero, you cannot find any particle occupying above Fermi level, or you can say the maximum value of energy that a fermion can occupy at absolute zero is the Fermi energy levels or the Fermi level. Okay, you may heard many places about the Fermi energy and Fermi levels. So this is the simple concept. Okay, now we can draw it and we can say that at absolute zero, all energy states up to epsilon f, that means up to energy Fermi energy are occupied, and none is occupied above epsilon f. Okay, so we will now this is at absolute temperature at absolute zero. We will look at different temperature, that is temperature higher than this one. What will happen? So and also we can draw it. First of all, you can draw the Fermi distribution function at absolute zero. How it looks? So actually it looks like a step, like this is your f d of epsilon, and this is 1 and this is maybe it is 0.5, because you need only the maximum value 1, because more than 1 you don't have any probability for the fermions to occupy. And here this is my epsilon Fermi energy. Now I will draw it. So this will be like this. That means up to the energy value epsilon f, that means up to Fermi energy, you have the probability of 1. After that, nothing, 0 probability. Okay, you don't have any. So this is at equal to 0 at absolute 0. Now, if you increase the temperature a little bit, again I am drawing here. This is my epsilon f, and this is 1, and here p of epsilon. Okay, so I will just make 0.5. One thing, whatever may be the temperature, I thought you have at epsilon f the probability is half, that we shown in the beginning. So we can take this point. This is the point where you are getting epsilon is equal to 0.5. And now, how we will draw it? We will draw like this is your 1, and increase. That means some of the particles are started to occupy above your Fermi level. Okay, when you increase the temperature from 0 to 0, you put T is equal to 0, 1, 0.1, this much temperature. You increase the temperature a little bit, and you are getting sorry, not this quantity, which is Kb, epsilon F by Kb. This much temperature you increase. If you increase the temperature further, so what will happen? Your particles will again and again occupy above the Fermi energy level. Okay, so that you started occupying more and more particles, and once your temperature is very greater than your energy is very greater than kBT, the things will converge to Maxwell-Boltzmann distribution function that we have seen in the beginning. Okay, so here again I am increasing. So this is f of 0 d, and this is your epsilon f, and this is somewhere here, this is 1, and somewhere here this is 0.5. Why I put 0.5, whatever may be the value, at epsilon f you have the probability of half. Okay, that you have to keep in mind always. So half will come. So this is the half point, midpoint, and once you increase the temperature further, so what will happen? You will have more and more particles started occupying the high energy level, and things will be somewhat like this. This is for P is equal to 1 into epsilon by Q. So this is the way how the particles are distributed for higher energy levels. That is, if a system contains n fermions, we can calculate its Fermi energy epsilon by F by filling up to its energy stage with the n particles in order to occupy energy starting from epsilon equal to 0. Okay, the highest state to be occupied will then have energy epsilon equal to epsilon f. Okay, so that we will get the Fermi energy value, so that you can get it. And now, as the temperature is increased above T equal to 0, but with kBT still smaller than EF. Okay, you have to keep in mind kBT is compared to EF, it is smaller, it is not higher. Okay, then the fermions will leave the stage just below epsilon f to move to higher state more than epsilon EF. Okay, and at a high temperature, fermions even at the lowest stage, that means at the lowest energy value EF, it started moving to moving above the epsilon F. Okay, and you can say what is called F of 0. That means here it just drops. So this one, okay, with higher and higher energies, and it just converges to Maxwell's distribution. Okay, I will just stop it here, and we will study a few more things regarding this, and we will discuss the black body radiation and all.